Professor Soumen Chakrabarti, due to some personal reasons, he could not come in person. So he is a distinguished member of the IITB faculty. He is a professor. He is a fellow of the Indian Academy of Sciences, also Indian National Science Academy, and also the Bhatnagar Awardee. And so he works on web search, data mining, and artificial intelligence applications kind of a framework are the other. Okay. So I think he will come on Skype. And
Can someone confirm by voice that you can see the slides on your screen?
Yeah, we can see your screen.
Okay. Okay. Thank you very much for your patience. And I really appreciate the opportunity to talk to you remotely. Today I will be talking about question answering and some techniques for analyzing queries in a way that's not very homogeneous, in the sense that different words in the query will have very different roles to play. And our goal will be to analyze these roles of different query segments or words. The motivation for migrating standard web queries to question answering or structured answer seeking is very obvious. Around 2012, a Microsoft study showed that at least 57% of web search queries mention some kind of entity or target type or category. And here are two examples of such query templates. Someone may ask, which scientists played the or Dolly was cloned at which institute? So you would have an entity that is grounded in the query, such as violin or Dolly, a relation like played by or cloned at, connecting it to an unknown entity E2, whose type or may be indicated in the query as well as T2. Another example is a little more complicated query template saying who acted as Bhaskar in Anand. So this gives you a little graph structured query where Anand is the name of a movie, E1, Bhaskar is the name of the role, and we are looking for the actor who is E2. And in this case, because the relation node M is connected with a typed edge called actor, the type T2 of E2 is implicit. How well do these queries work on standard web search engines today? If the relation is relatively simple, there are only one or maximum two relations, and the entity E2 is well known, then things work out reasonably well because E2 is extracted not necessarily from a large web corpus, but from a large knowledge graph like Wikipedia or Freebase. If today you ask Bruce Willis movies to Google, you will get an excellent display of um, a lot of Bruce Willis movies, presumably ranked by overall ratings. That is because this query is captured by vertical search engine which specializes in movies. If you now change the query subtly to funny Bruce Willis movies, you will see that the rank order changes, but that's primarily because the genre is identified as comedies. Funny and comedy is somehow bridged by the search engine, and that means that when precise metadata about entities can be extracted ahead of time, these kinds of soft select queries get good responses. But this experience does not easily generalize to queries which stray outside these strict verticals. If instead you try to ask, find me a rugged laptop that is Linux friendly, the ranking between such laptops is no longer as clean or useful as in the movies vertical. Here are some more queries to establish that point. If you start with a relatively tuned down query like which phones have unsafe batteries that I should avoid, as you can see, even though Google knows very well about a list of standard phone models and manufacturers, and presumably Wikipedia has a page dedicated to every major phone model line, uh, the search engine does not surface specific phone brands or makes. Instead, there is a bunch of organic responses talking about why phone batteries explode and how we can prevent it, and so on and so forth. So at this point, you might detect that the vocabulary of the web in talking about unsafe batteries is a little exaggerated. People start talking about exploding batteries or phones. It's usually not near that extreme. But in any case, you change your query now, learning from the language of the web to exploding phones. And this suddenly gets you a little closer. But it identifies the brand or one of the problematic brands, but does not yet really surface the models. It says reviews of the Note 7, but Samsung Note 7 has a Wikipedia page. It has a previous entry. It has pictures. And unlike in the movie situation, you don't get a structured call out of that model. Now you take Google's queue and say which phone was exploding. And even here, you see that the highlight, Samsung exploding phone, it fails to satisfy the core of the query, which is which phone. And Galaxy Note 7 itself, 2 lines below, is not even highlighted. So why is that, right? Here are more, so what you really want is a display of the actual phone models with their Wikipedia pages or their discussions in GSM Arena or other knowledgeable websites. In fact, alternative queries suggested by Google contain a lot of the correct phone models, and yet Google does not surface the specific pages for these models. From an earlier slide, you ask, Dolly was cloned where? If a human understands what it means to clone, even if they're not totally aware of who or what Dolly might be, um, the meaning of where is very clear. What kind of place can a living organism be cloned in? It's usually a laboratory, some sort of a research organization or institution. But if you say Dolly was cloned where, the top call out is actually about some life history of Dolly, which presumably contains the name of the institution in the whole text, but pulled out. Instead, you see Dolly and cloned highlighted. But those are information provided in the query itself. Those are no words, and the user would like to instantiate where, just like the user would earlier like to instantiate which scientist in the file. So that doesn't happen. And then you become more helpful and you say Dolly was cloned which organization or Dolly was cloned in which organization. And the top call out, top response is just Dolly's page in Wikipedia, which is enough to get that information, but it doesn't extract it as an entity and return it directly to you. And now if you are even more helpful and you say Dolly was cloned which institute, then finally, thanks to the literal matching of the word institute, you find Roslin Institute in Midlothian, Scotland, and this is it's less than what you'd like. You'd like to get like to avoid this kind of brittleness, and instead of falling off the structure cliff, you'd like to kind of slide down the structure ramp. You'd still like to extract maybe the Wikipedia page or this institute in the end. So for the purpose of this talk, we will consider a knowledge graph as consisting of a hierarchy of types in which there may be research institutions, persons, physicists, and so forth. And then these types would be connected to entities, such as the entity called Albert Einstein. And any entity that belongs to physicist by transitivity belongs to person, entity, and so on. There may be also binary relations between these entities, as simple edges, such as there's a book which is authored by a particular person, or a person is born at a particular place. So largely we can think of the knowledge graph as a standard graph, and we'll only look at binary relations for most of these, or all of this talk. General relations would be hyperedges, or which can be approximated as stars. Now, the knowledge graph is useful. It's usually sound, but it's very incomplete. In particular, if you ask in which band did Jimmy Page perform before Led Zeppelin, the knowledge graph may have a list of bands connected to the artist Jimmy Page, but it may not have record the relative dates during which he performed in those bands. So that's why the knowledge graph is incomplete, and supplementing information there with information from a large corpus may be really useful. So let's look at a particular query and see how the knowledge graph and the corpus can together help you answer it accurately. Suppose the query is losing team baseball World Series 1998. This is the way in which typically people type queries to a web search engine, because the web search engine doesn't really pay too much attention to the connective language yet. Perhaps the natural language expression of this information need would be uh, who was the losing team in the baseball World Series held in 1998. But so if a human, on hearing that more elaborate query, or even this what we call a telegraphic short query, would say, okay, clearly the user is looking for a baseball team, right? And everything else in the query is qualifying what kind of baseball team or which baseball team the user wishes to pinpoint. But an automatic system may mistakenly think that World Series is the target type, right? You might say, in which World Series did something happen? And if you did that, in any large type catalog, query words would match some type or the other. For example, if you try to look around in your knowledge graph for teams which match World Series, you would readily find World Series hockey teams. If you took that path, you'd of course branch off into weird places in the knowledge graph which would not correctly answer your query. On the other hand, if you correctly identified that team and baseball are the words characterizing target type, then you would locate a canonical node in the knowledge graph which corresponds to the correct type of Major League Baseball teams, of which among hundreds of other candidates would be this one candidate, the San Diego Padres. Now, how do we know that this should rank higher than so many other Major League Baseball teams? Because San Diego Padres is mentioned in thousands of snippets, textual passages in web documents, which also mention words like World Series and losing in 1984 and 1998, and recall that some of those important green words also appear in the query. So this is basically the first demonstration. There will be more of the fact that different query words have different roles or colors. But unfortunately, when the query comes into the system, there are no colors. It's just a string of tokens, and the search engine has to somehow divine the purpose or role of different query tokens and spans, and use that role information to match the knowledge graph or the corpus in very different ways, employing very different scoring functions. Observe that losing at World Series 1998 directly match passages in the textual corpus, whereas the only reason that team and baseball matches this particular passage is because of the occurrence of Padres, which goes through a relatively long inference chain through knowledge. So this is a non-trivial inference cycle which goes through the KG and the corpus, and we need to discover the roles and score them accordingly. We'll start with two roles, namely target types and everything else, and gradually we will refine our notion of query structuring. So, so we'll paint a generative story of how such queries can be created. So in probabilistic information retrieval, it's very common to say that instead of starting with a query and then finding a document which responds to it, let's look at a document and see how likely it is to generate the query instead. And then using Bayes' rule, we can flip it around and thus score documents in response to queries. So here is the upfront generative story. So first, there is this type description language model. This is the language that people use to describe various types. For example, the abstract notion of a nuclear scientist is described using the text, maybe I don't know, atomic scientist or nuclear scientist, and so on. So that's the type language model. For each of the T types, there is a certain distribution over words which describes that. Now, for each query, so which scientists played the violin, we will proceed to write out the query as follows. First, every entity which is a candidate responds to the query, EQ. every entity in it has its own language of describing it. Einstein was a scientist, Jagadish Bose was a scientist. There are different languages or language models or distribution over words to describe these two scientists. So imagine that this plate marked by EQ is basically a stack of all possible scientists. And for every scientist, there is one plate. And for every scientist, there is a distribution theta, which is used to describe that. Okay. And this is quite, for simplicity, we don't make it global, although you could also have a global E. And this particular Q selects a subset of these generation models about entity descriptions. Now, here I said this story will be back to front. So the answer would come before the question, sort of like Hitchhiker's Guide to the Galaxy. 42 is the answer, then what is the question? So suppose Einstein is the answer. Now the question is, how can you ask about Einstein in a way that parts of the query hint at the type of Einstein or some types of Einstein, and other parts of the query correspond to describing certain specific properties about Einstein, such as that he played a violin. So first, we will choose to describe Einstein. Now, Einstein has many types, but if you are going to ask a query whose answer is Einstein, you probably wouldn't say it's a biped mammal who played the violin, right? It's more natural to say who's a scientist or who's a theoretical physicist who played the violin. So you sample that word distribution, and so that whichever type we're going to transcribe that into words in the query. Now we start writing down the query word by word, and for each word there's this big switch. We can go one of two ways: the red words and the green words. If Z comes out to be the red words, namely the type revealing words, then I am going to sample from here. If on the other hand, so I'm going to use the type, then I'm going to sample corresponding type distribution from here. Whereas, so that sample thing which scientist. Whereas if Z turns out to be other green words, then I'm going to say other specific things about Einstein, like played the violin. Right? So this is going to happen as a confluence of all these random variables which you haven't seen. So all the unfilled nodes not seen. What you finally see is the word that was created. This word happened either because Z was red and we used the type specific distribution and the type I chose, or because Z was green and I used green words from down below. If you write this process down as a probabilistic equation, you'll get a fairly simple thinning down or conditional independence assumptions, which I won't go into. But you can put this into a suitable discriminative feature-based classification strategy as well. And again, I'll skip the details because the much better models are coming up soon. So this model really just captures a two-way distinction between query tokens, target type, and everything else, red and green. So we can run through this, but it's not too important. The important thing is that we could do this sort of scoring either in a generative way where there are probability estimates, or we could do it in a discriminative way by saying that the good entity should beat all the bad entities and train it sort of like support vector machines, except there's a complication that not all features are observable at training time. People typically supervise the system saying which scientist played the violin, Einstein, which scientist played the bongo, Jeff Fine, so on and so forth. So here is how do I turn everything into the red and green word? So that is not supervised. Now, this is a preliminary sketch of what happens if you build such models on the query segments. The lower line here is a generic search engine which doesn't understand types of entities. So just at snippets which look promising from text match standpoint, and then extracts these from there, does history or frequency-based voting, and then pushes the best scoring entities to the top. The upper envelope in gray is where a human manually provides the target type. So this is very painstaking. You have to extract the target type from a knowledge graph with thousands of types. If that is done, the human may not be perfect, but the human is close to perfect. So you could regard the upper line as some sort of a speed of light. It's hard for systems to beat that line. Now, what happens is the generative model significantly improves on the genetic search engine. It fills about 28% of the gap to the human performance, and the discriminative system fills 43% of the gap to the upper envelope. So generic worse than generative, worse than discriminative, worse than human, which is sort of what you expect from standard machine learning principles. Our next step, though, is that we're kind of dissatisfied with splitting up the query into just the red part and the green, because the green part may have a lot more detail. So queries will seek answer entities E2, and it will have embedded or grounded entities E1 like violin, or in which cities did Einstein teach, so that then Einstein would be E1, otherwise violin would be E1, seeking answer entities, which scientist, or in which institute was Dolly cloned. So that's T2, which may be explicit in the query, or may not be. We'll see examples later on where T2 is not very explicit. Now, the query may also try to make hints about the relations that connect E1 and E2. From which college did Obama graduate? So, graduate and from would comprise the relation. And then there could be selectors, which are like a default option. If we cannot structure some tokens in the query as part of the knowledge graph mapping process, we could say instead look for selectors in a corpus passage and try to make the best of it. For example, if we say Dave Navarro's first band, clearly Dave Navarro is E1 and the T2 is band, although what kind of band is an interesting point because band could be frequency bands, radio waves. It could be like a band saw or something like that. But it's only because we know who Dave Navarro is that we can infer that band is likely to be a musical band. So there is an important bridge required between the string representation of T2 and the abstract symbolic ID for T2. I won't go into details of that, but that's a very tricky step as well. But as you can see, that there can be many noisy interpretations with overlapping labels. It's hard for even a human to say what all these things should be. And in fact, that you can't really bucket a word into one role because there could be a relation hint in band as well. Whenever you see names of celebrities or well-known artists and a band, the predominant relationship is one of participation as a musician. The predominant relation is not, for example, sponsored the band, right? Or being a security guard for a band. Those are more obscure. So the relationship may also be implicit in either E1 or T2. So there are all these noisy interpretations. One of the key innovations in our work has been that instead of choosing and putting one interpretation and then asking that interpretations from a structured knowledge base, we keep our promising interpretations and we score and rank target entities E2 as some sort of a Bayesian average of how many and how good interpretations support E2. So here is a second level model which gives a quick cartoon of how that might be done. Segmentation of the query is a random variable, and of course this is a very high dimensional, many option random variable because there can be lots of segmentations of a longish query. That segmentation, however, leads to a hint to a target type. T2 is the abstract ID. It's again not known, just like ideal segmentation is not known. So T2 is an ID in the knowledge graph, but how do you segment it? If you choose a specific T2, then there has to be some sort of a clue that the segment you chose to represent T2 matches the abstract T2 well. That people often talk of that type with those strings, like nuclear physicists or which scientist. Similarly, there has to be a scoring mechanism between a relation pick. Any span in the query will designate the relation. And finally, entities that are grounded in the query also have to be identified at that stage and matched to their string counterpart in the query. Things which don't match any of these things are left as string valued query words, which will be matched in the corpus instead of the knowledge graph. At the bottom, we will fix or observe or instantiate E2s one by one. So we'll pretend we know E2, and then we will evaluate some sort of a joint probability of the whole graph being set to those random variable values that we think they are. Right? So there has to be some sort of a belief measure that the E2 we have chosen belongs to the T2. Now, if E2 is already well known and in the knowledge graph, then whether E2 belongs to the absolute target or not is known as 0 or 1. But in reality, as I said, most knowledge graphs are incomplete, and there is a host of other techniques from open information extraction and knowledge-based completion, which can give you softer, uh, uncertain, but very useful partial signals as to whether you think E2 is a T2 or not, especially for cases where E2 is not that well known. So that's that particular score. Similarly, we would like to have a score for whether E2 and E1 are connected through the indicator relation. Did Obama really get born in Hawaii or Nigeria? So the relation has to be witness to that. And finally, for things that where the KG is helpless, the knowledge graph is unhelpful, we would be looking for corpus snippets which mention E2 definitely with some of the selectors, like Dave Navarro's first band, right? So the first may be coming from the corpus, and then the specific band should be ideally mentioned in the snippet. Otherwise, we don't know if this is talking about even the same Dave Navarro. So depending on how you score things, this particular scoring node have degrees between 2 and 4, and you can take it with various doses of salt, depending on how your learning system is designed. I'll skip these details about how the language for describing types and relations is designed for lack of time. And instead, I'll sketch how corpus snippets are captured. So that's done using standard information retrieval engine. Then we extract a whole bunch of features like, do E1 and E2 both appear in the snippet, with what lexical distance, what is the relation phrases between them, how well does it cover the informative words in the query, the so-called inverse document frequency, which measures how rare a query word is and therefore how presumably informative. But so instead of going directly into results of this second step, let me start by pointing out the shortcomings. The main shortcoming is that segmenting or hard segmentation of the query into these four pieces, T1, T2, R, and S, results in combinatorial explosion. And in fact, the roles of query spans are not mutually exclusive. Consider these queries: who discovered penicillin and who discovered Antarctica. Who is a very weak clue. Who might mean a person, it might mean a sports team like who won the match, or who exports the most oranges in the world. That's in fact a country. So who is a very weak clue. Discovered is getting better, but a lot of things are discovered. The main clue to T2, the target type, actually comes from penicillin or Antarctica. If a human knows what penicillin is, and then the human has a fairly good shot at what kind of person might discover penicillin. They may not be able to verbalize it very well as a string, like it could be a doctor, it could be a biochemist, it could be a chemist, we don't really know, but some area of semantic space from which discoverers of penicillin might come. Similarly, discoverers of Antarctica will come from some entirely different. So that's why we think this hard query segmentation, as of 2015, we sort of knew that that's not a very good approach. So what we need is some sort of a diffused clue spans in queries. So say baseball team lost World Series 1998, we want to say that the strongest type is baseball team. But the fact that the baseball team played a World Series may subtype your baseball team and narrow down your focus, and that's important. E1, right? So let's say E1 is World Series, or you might faithfully include 1998 because it's a specific instance of the World Series matches. So again, there should be greater belongingness, right? World Series may now be a hint to both E1 and T2, right? We don't want to disable it. We don't want to hard segment the query. And similarly, R might say that, the team lost, and that's sort of the rating connection in the knowledge graphs. There's a team which won and San Diego Padres lost. And this was a match which happened in 1998 and was a member of World Series and so on. So lost is a very heavy clue, but team is also a clue of the relation, right? And so we'd really like to have these overlapping evidences to different roles of the query. So accordingly, around last year, we built a new question answering system which doesn't try any segmentation and instead applies a battery of neural networks on the query, each with the purpose of isolating clues for one of those roles. So first, the query goes to an E1 linker, which finds E1, such as World Series 1998 or played the violin, so violin is one of those. Then that E1 is sent to both a knowledge graph and a corpus. And remember that the knowledge graph looks like a graph where some of the nodes are these E1s, and the corpus is our usual streams of text, except that some texts are annotated with canonical entity IDs. The technique for doing that is basically the talk, and I have the line of projects which is trying to improve the accuracy of identifying and disambiguating specific entities in unstructured text. For example, if you see young Albert took music lessons from the age of 3 years, you'd still like to figure out that this Albert is not Prince Albert in England, but this is Albert Einstein who played the violin, maybe from other evidence in the same document. So anyway, this E1 or E1s go to a knowledge graph and corpus simultaneously, which then explore around the occurrences of E1s. And thus, we get a bunch of relations which are incident on E1. We see what types these E1s belong to. Remember, many E1s belong to multiple types. Obama is a politician and an ex-president and a leader and a Democrat and a professor and a father and a husband and so on. And similarly, the corpus also gives these candidate E2s along contexts in which E2 appears, possibly with E1s and other tokens of the query. Now, once we have these candidate E2s lined up with their types, the connecting relations, and the text contexts, we have one convolutional network which tries to find if there is in this relation R anywhere in the query. We're not bothered with exactly where, or delineating the boundaries of that clue. Similarly, another convolutional network finds if there are segments in the query, fully overlapping with the first one, which hint at type T. And then there are these stack of contexts, one applied to each context with the same parameters. But these three parameter sets of three contexts could be radically different. So this particular context tries to find out if there are good matches, like prior to his work in Led Zeppelin, Jimmy Page, etc., right? And then you see Jimmy Page first, and prior some match, and the sufficiently well-trained word embedding together with good cognate should find a little blip of evidence over there. So that's what these corpus cognates do. And once we have evidence of corpus matching, type matching, and relation matching lined up, we aggregate over all the corpus snippets and then do a score combination. So this is yet another neural network, not a very simple one, a single layer one, which learns how to merge the scores of these three somewhat disparate evidence scales and see how to blend them together. Once we scored all the candidate E2s, we can rank them. So the scores of E2 and rank it, and then because at training time the gold E2 stars are known, we make sure that E2 stars ranks which are above everyone else, and so scores which are larger everyone else. If not, it's a loss that is used to crop and train more of these networks. Okay. So to give a slightly more symbolic what we are doing, the labeled instances, remember, are queries with gold entities E2 star. But the gold interpretations are not provided. So there are these two approaches based on the definition of what we mean by an interpretation. In one, we think about the interpretation as a structured query which is executed on the knowledge graph to give a set. And then we compare the set E2 against the gold set E2 star, and then we get a set oriented view we call precision in F1. The other is to actually make E2 part of the interpretation. And then your output is not really a set of E2s, but a ranking over all the E2s. And then we can use some surrogate of the ranking loss, like area of the curve or mean average precision or normalized discounted cumulative gain, such as are widely used in information retrieval community. So the main point of ranking good and bad entities is that every good entity should beat every bad entity, and that can be written down as, so how do you know that the good entity has beaten the bad entity? Now that is quantified universally over all possible interpretations. So what we want to say is that over all possible T2s and Rs and possible S matches, which you're not showing here, the best score of E2 plus should be larger than the best score of an E2 minus, which is a wrong response entity. Now, one of these maxes on the right-hand side is fine. That doesn't break convexity. But the left-hand side max breaks convexity. So over best interpretation of E2 plus and E2 minus. And then to get around the non-convexity problem, we do a iterative optimization and annual between two convex optimizers with no global guarantees, but it works reasonably well in practice. For details, you can look up our paper. All this is non-convex is found that these kinds of optimizations with latent variables in the context of question answering works reasonably well. So I'll talk about two data sets, one published from the Trek conference, the other recently released in 2013 from Stanford, called Web Questions. Web Questions was prepared so that 100% of its queries can be answered from the knowledge graph alone, whereas about half of the queries in Trek can be answered by the knowledge graph. So that is the dataset that will show off how corpus evidence can supplement knowledge graph evidence very well. And also, we explored a broad spectrum of query syntax. So for every data set, we actually express the query as if it was a keyword query asked to a search engine, sort of telegraphic, and also long-winding, very explicit natural language expressions of information. And that was to kind of expose earlier work which heavily banked on traditional natural language parsing of the query sentence to figure out the structure in it. We do not want to be that sensitive. We would like to be relatively robust and insensitive to the amount of syntactic validity in the query. So as you can see here, first observation is that if we use both knowledge graph and corpus, our ranking accuracy is uniformly larger, sometimes much, much larger. The precision of trend increases dramatically for most of the 4 settings. Also observe that for Trek INEX, the Trek dataset, KG by itself is doing really badly. And we know why, because about half the queries can be answered by KG alone, and corpus alone is better than KG. The combination is the best. Whereas if you look at web questions, because we designed the queries it's answerable from the knowledge graph alone, naturally the corpus is not doing that well. But again, if you slap together the information from both of them, that gives the best performance. So this kind of validates our hypothesis that a cooperative evidence mixing is essential to solving question answering problems well. Now we come to this extension of the earlier recall precision or the NDCG plots you saw in terms of accuracy of answering queries. If we do no interpretation of the query, we look at the query as just a keyword query, then we get, as expected, very poor accuracy scores or ranking accuracies. If we use the type plus selector formalism for the query, like some words are red and some words are green, that gives the second step. Okay? Whereas if we do a discriminative learning or we do a hand-done grid search of the full model, then we get larger accuracies. But these grid search and availability were still for query partitioning or query segmentation strategies. So the neural numbers have not come in yet, and those are here. So the segmentation approaches are unhighlighted. The neural approaches are highlighted in green. So as you can see, there's again a big jump as we go from segmentation-based mapping schemes to the overlapping smooth neural evidence merging scheme. that gives us the best numbers to get. And also, if we compare with systems by other users, we see that we are in terms of even F1 scoring. So far we're talking about ranking performance. But if we start comparing those columns and somehow turn our system, AccuCN, using a cutoff, be a set retrieval system, which is not best used, we are still pretty close to the top. We are at the top and far beyond the competition for 3 configurations: track data with both keyword and natural language mode and web questions in keyword. We are way above the others. And in case most researchers have looked at today, this situation is super optimized by others, we are at like third rank. However, uh, if you can ideally threshold on our ranking and cut it off at the perfect place in retrospect, then we have a number far better than others. So this basically means that we are very good at ranking. We are just not so good at cutting it off to 50%. So if we can improve that, we have a promise of being even the best over here. So now I'd like to finish up with some recent work we have been doing in collaboration with IBM. And that is to extend this of only 1 or 2 relation queries to complex multi-step queries with join, arithmetic, and logic. So this is where we see question answers going this year and next year. So there are all queries you could try on Google. If you try often enough, they'll probably notice it and fix something. But if say Manuel Blum Sun College, this query will work very well because Google can 2 hops on the knowledge graph go from Manuel Blum to his Navin to Navrin's college, which would be the college where he went for education, like MIT, or the college he teaches now, which is Carnegie Mellon, or maybe it's moved. But if you change the college where Manuel Blum's relative teaches, the second query doesn't behave anywhere near the first. So again, this notion of brittle. So we would like to answer queries like this very well. If you say movie directed by Bernard Chazelle's relative, again the solutions are that eye-catching. Now, ideally, what we'd like to do is to learn to translate complex multi-step or multi-clause queries into something that looks like dialogue, except it might have textual clauses in it. So we'd like to say Bernard Chazelle's Fibly is related to some R, who is a person, and R directed M, where M is a movie, and then retrieve M. That's my final answer to this query. If I'm trying to find companies that make fanless motherboards, I'd like to say M is a motherboard, M has attribute fanless, and C makes M. Please retrieve C for me. This one, the third one is particularly risky. If you say cities where Einstein taught, people don't teach cities directly. So Einstein taught at U, and U is located in C. So you have to infer that there is this 2-hop reasoning going on. And perhaps inferring the type of U is not that difficult. U has to be some educational institution because Einstein is teaching there. The next one is particularly difficult. The age of Satyajit Ray, Sukumar Ray's dad, when Sukumar Ray died. Right. So basically, the query amount Satyajit was born in year 1, Sukumar died in year 2, and the answer is year 2 minus year 1. So we have to start doing arithmetic. And then sort of queries in a continuum of difficulty, such as list all the rivers in India. That's pretty easy from the knowledge graph. List all rivers in Brazil. That's pretty easy. Now, if I ask which country has more rivers, Brazil or India? It's not clear what I'm asking anymore. And it's not clear, even if a search engine gets it right, that it gets it right for the correct reasons. And then you might ask, which countries have more rivers than India? This is really difficult. And finally, if we say, how many countries that have more rivers than India? Now there's a count on top, right? So there's comparative operators, there's joins, there's arithmetic. You could look at this archive paper for a nice catalog of a hierarchy of structural query complexities that we would like to answer in the short term. I'm running out of time, so I'll only skip very rapidly through the kind of things people are trying. So the paper from Berkeley, I think in 2016, which tried to use a neural network to assemble a neural network, which would be like fitting together various operators in the expression tree and then be able to answer queries by running that expression tree. Another technique is to digest the query, like largest city in the US, and prepare some sort of a continuous or neural memory module, and then in a sequence generation model, um, generate a series of clauses which access this memory and prepare not the answers, but a program which you have to run to get the answers. So there's a particular programming language which only allows straight line execution. Every line looks like new variable declaration equals a sign, a function of existing variables. And initially variables are seeded from things in the knowledge graph, say. And you are supposed to build up this series of expressions so that if you execute them in a suitable machine or abstract machine, you'll get the correct response, such as if you say largest city in the US, that might mean population, it might also mean things like area. But New York City will be one of the possible responses based on population. Now, this is a very difficult game because the neural network is fully in charge of translating from natural language to a structured program. And only when the program is executed, we give it extremely distant rewards to learn whether it did the entire translation right or not. So training these things is very tricky, and we are working on curriculum learning and other type-based constraints to try to teach the system how to transcribe natural language into this complex multi-clause queries. Okay, so the summary and outlook is that question answering must use both knowledge graph and corpus. The knowledge graph gives a lot of valuable structuring, it's very low noise, but it's also low coverage. The corpus, on the other hand, mentions a lot of things in passing, but it's unstructured and noisy. So how do we structure the corpus at that time, offline, so that it can be coupled to the knowledge graph in a very natural way, and then used in a joint, neural or other learning system to rank the evidence in favor of each candidate. Query understanding is improving rapidly, but it's still brittle. And what we need is like a schema-like syntax agnostic evidence aggregation. So multiple clauses could be involving a particular entity, and some of those clauses may touch the graph, some may touch the corpus. We should not kind of assume that all the evidence come from one place or the other. We're able to pick and choose as best we can. And decomposing a complex query into sub-goals or sub-tasks, and then assembling the answer using relational logic, arithmetic, Boolean expressions, set expressions, this is still a major challenge. So that's the end of my presentation. I'd be happy to take questions.
Thank you.
Yes, perfectly.
Soumen, this is Chiru here.
Oh, hi, you have heard the talk. What are you doing here?
Yeah, we are missing you. So, very nice talk. So, can you have your comments on, see, as you said, that to do this complex question answering, right, you need these knowledge graphs.
Yes.
Right. Now, to deploy reasonable systems, so what is your sense? How far are we from even getting those graphs up and running? I can understand that companies like Google or Amazon may have it behind them, but for example, like in open domain, like how far are we from getting knowledge graphs in place?
So knowledge graphs are always work in progress, and different agencies may have them to different states of perfection, but no one is nearly perfect. So there's this entire area of open information extraction that researchers like Partha Talukdar and Mosam work on, which basically bootstraps approximations to knowledge graphs from unstructured text. Right, so if you just read through a web-sized corpus, it's fairly easy to discover relations like antibiotics kill bacteria, right? Or hammers are used used on nails, and so on and so forth. So, or that Einstein was born in Ulm. So extracting this kind of information from unstructured text has been a 1.5 decade long journey. And as you can put together a lot of such structured information from unstructured text. So there are, of course, some caveats in that people don't state the obvious. So if you base the construction of knowledge graph only on explicitly mentioned text, you may believe that all sheep in the world are black. There is no white sheep. Or that all carpets are red, they never make carpets of other colors, or that all bystanders are innocent, right? So there's always a danger of not discovering common sense knowledge because people only state the remarkable. But modulo that, I think there are enough techniques to get started. There are ways to identify named entities in text. There are ways to do coreference resolution or record linkage to cluster those entities into what look like canonical equivalence classes. And then once you do that, you can start like an entity resolution system, which then ties those canonicalized IDs to other new text. That's how you bootstrap these systems.
Right. Thank you.
Any other question? Thank you, Soumen. So I think I will send the momentum as then pass it to you.
Oh, that's fine. Yeah. I'm very pleased and honored, and please accept my apologies for having to talk remotely.
Thank you.
Thank you, and bye.